Hello, everyone. This is the screencast for section 6.4 in our textbook, Chi-Square Test of Independence. You're going to need the TigerStats package, so make sure that you have libraried it before you begin. I want to first do a little review, something way back in the beginning of the course. How do you study the relationship between two categorical variables? For example, suppose that we take a look again at the Math 111 survey data frame. So let's go ahead and copy these 2 lines of code and head to our studio and enter them. So we'll get a view of the data frame and we'll get help on it. And what we want to look at this time is, let me check, so we want to look at 2 variables, sex and seat. So, sex is your sex, male or female. Here in the help, what sex are you? And seat is when you have a choice, where do you prefer to sit in a classroom? And so remember, sex, somewhere over, yep, here it is, has the values male and female, lowercase. And seat is 1 underscore front, 2 underscore middle, and 3 underscore back. It's just the way the responses were written into the data frame. So those are 2 categorical variables. Now, remember, when we're studying the relationship between 2 variables, it's often convenient to view one of them as an explanatory variable and the other as a response variable. Now, the explanatory variable is going to be the variable that we think might help to cause or help to explain the values of the response variable, or that might be used to predict the response variable. And so here, I'm going to figure sex as the explanatory variable because I think that a person's sex could determine the kind of cultural conditioning they get that might ensue in them having particular preferences in their seating. I don't think it goes the other way around, anyway. I don't think that where you sit helps to determine your sex. Now, I have no idea if sex is really related to seat, but it just seems convenient here to think of it as the explanatory variable. So when you investigate and you want to make a 2-way table to investigate the relationship, you put the response variable twiddles the sex variable as your formula. Of course, you have to say what data set the variables live in. And in tallies, it's good to get totals with margins as true. So we found there were 40 females and 31 males in the sample. And we see that of the 40 females, 19 of them, which is about half, preferred the front, whereas only 8 out of the 31 males preferred the front. And we can read the other numbers in a similar way. Now, if you really want to check for a relationship, then you can't rely just on the raw numbers themselves because the 2 group sizes are different. There are more females than males in the sample. So you'd expect the numbers in the female columns to be bigger than the numbers in the male columns just because of that. So it's really best to correct for that by computing column percentages. And that's done by adding the format equals % to your function call to tally. And so now you can begin, as we learned back early in the course, we can check on the relationship by looking for big differences in the row percentages as you go across a column. And so I see that 47.5% of the females preferred the front, but only about 25% of the males preferred the front. That seems like a big difference. And there are other big differences that you could focus on. It looks like 12% versus 22%. Males were twice as likely in our sample to prefer the back. So there are these ways that you can describe the relationship using some of the big differences that you found. And so you might say this, that in the sample, sex and seating preferences are related, and you back it up with some numbers you found. For example, females were more likely to prefer the front than males, 45% versus 25%. So you cite the numbers that help you can help convince you of the relationship. So kind of to summarize that, you make your column percents, you compare those column percents across the rows, not down a column. That would be meaningless. And if you see one or more big differences, then you figure that maybe those two variables are related. In other words, the grouping variable, the explanatory variable, makes a difference in what you see for the response variable. Now, if you don't see any big differences in those column percentages as you go across a row, then you figure that maybe the two variables are independent. You know, in this table, what if there had been really no difference in any of the column percentages? Then that would mean that the percent of females who prefer the front is about the same as the percent of males who prefer the front. So it doesn't matter if you're male or female to where you prefer to sit. So if all the column percentages are, if all the column percents are the same as you go across the row all the time, or if they were close to the same, then you're kind of thinking the two variables don't have anything to do with each other. Knowing somebody's sex really doesn't tell you much about where they're going to prefer to sit. Independence. Independence. So the whole question is whether the two variables are related or independent. So how do we do inference for this kind of situation? You know, we can look at the data and make a decision about what the data is trying to say to us, but what does it really say to us about the population from where the data comes? That's the statistical inference that we want to do. So, like in the sample, we saw that sex and seat were related in the data. The males were less likely than the females to prefer the front. They were more likely than females to prefer the back. But what about the population? If we could somehow get everybody in the population into our sample and make a tally table, would we see differences like that? After all, the sample was picked randomly from the population. It's a matter of chance which students got into the sample. So could it be that the pattern we saw in the sample was just due to chance variation in who got into the sample? Or is that pattern that we saw in the data so strong, so big, 45 versus 25% or something? Is it so strong that we really ought to conclude that there is a relationship in the population? That's the inferential question that we're asking ourselves here. So because there is this question, we could set up hypotheses that express possibilities for how it could be. The null hypothesis here is going to say that sex and seating preference are independent in the Georgetown College population. And the alternative hypothesis is going to say, no, they're related. Now, how do we proceed from here? In a test of significance, you're supposed to eventually come up with a test statistic, and from that compute a p-value, and use your p-value to decide whether to reject the null or fail to reject it. So we have some work to do. How could we come up with such a test statistic? Well, my idea is to find out, what sort of two-way table would a believer in the null hypothesis expect to be seeing out of a sample of 71 people from the population? Once we can figure out what an expected table looks like, then maybe we could find a number that measures how different the actual table is, the one we actually saw, how different the actual table is from the table that the null expected. And that number will be our test statistic. And once we have the test statistic, we can find the p-value. What's the chance of getting a test statistic at least as big as the one we got if the null is right? And once we have the p-value, we can use it to decide if we've got strong evidence in this data for a relationship between sex and seed out in the population. Okay? So, we have the observed table, which I, for some reason, don't have in these slides. I'll fix that. That's the table that we were looking at back here. But what would the null hypothesis that believes that sex and seeding preference are independent, what would the null hypothesis expect to see for a table like this based on a random sample of 71 students? Well, there's actually an R function that will help you compute that. It's called exp counts. And if you were to apply it to a table that you had created, a little tally table you had created, then it will give you the null's expected table. Now, these are little fractions here, so let me interpret it for you. If you believe in the null hypothesis, then when you see a sample of 71 students, you would expect about 15.2 of them to be females who prefer the front. You would expect about 11.7 of them to be males who prefer the front. Those are different numbers there because remember, there's more females than males. Now, of course, you're not expecting to see exactly 15.2. You can only see a whole number of females. But you're expecting to see around this number, give or take, some for chance variation in the sampling process. So, why does the null hypothesis expect to see that particular table? The reason is that the formula for computing the expected cell counts has been carefully designed so that if you took the column percentages of those expected counts, they would turn out exactly the same along every row, no difference at all. And if there's no difference at all, remember that means females and males equally likely to prefer the front, females and males equally likely to prefer the middle, females and males equally likely to prefer the back. Knowing somebody's sex wouldn't tell you a thing about what they prefer. So that's how that's why the expected cell counts were computed the way they were. Now, there's actually a formula for how they were computed. What you do to get the expected count in any cell is you take the total of the row that cell is in, the total of the column that cell is in, and you divide by the total number of people in the sample, which is called the grand total. So, for example, here's our table. And if you wanted to find the expected number of females here, according to the null hypothesis, then you take the row total, which is the 19 plus 8. You take the column total, which is the 19 plus the 16 plus the 5 going down this column that contains this cell. And you divide by the 71, which is all of these numbers added together. And that's how we got that 15.2 in the expected cell counts. So don't worry, the computer is going to compute these expected counts for you, all the time. Maybe there'll be like a little homework exercise where you'll have to compute an expected count, just once, just to show that you understand where it's coming from. But the computer's going to do it for the most part. And here's the other thing. As far as the test statistic, all it has to do is figure out how much the whole observed table differs from the expected counts table that the null has in mind. And so what we could do is we could just add up the difference between the observed count in a cell versus the expected count in a cell, square it and divide by the expected, do that for all of the cells. And what you were creating is that same chi-square statistic that we worked with in the last section. So our test statistic is going to be a chi-square statistic again. And so, like, you could use our like a calculator and you could find out what it is. You'd have to, work with every one of the cells in the table, and there are 6 cells. So the observed 19 females that prefer the front compared to the 15.21 expected according to the null hypothesis, squared and divide by 15.21. And that's a fraction. And there's going to be 5 more fractions that you would need to compute. It turns out the total is 3.73. But don't worry, R is going to compute those numbers for you off of the data. What we're interested in really is that 3.73, is it an unusually big number if the null is right? What's the chance? What's the chance of getting 3.73 or more if the null is right? So what we're looking for here is a p-value, okay? To get that p-value, we're going to have to know something about how the chi-square statistic behaves as a random variable. And there is, fortunately, some statistical theory to help us out. It says, as long as the sample size is big enough, we'll talk about what big enough means in a bit. And if the null is actually right, then the chi-square statistic has approximately a chi-square distribution, one that's given by one of those chi-square curves we learned about. And it'll be the curve where the degrees of freedom is equal to the number of rows in our tally table minus 1 times the number of columns in our tally table minus 1. And we've learned that the chi-square distribution has an expected value that's its degrees of freedom. So what we learn is if the null is right, then we would expect the chi-square statistic to be about the degrees of freedom, give or take some for chance variation in the sampling process. Now, how big is big enough? The stat theory says that the expected cell count should be at least 5 in order for the chi-square statistic to have this chi-square distribution with the specified number of degrees of freedom. Now, our table had 3 rows, front, middle, back row. It had 2 columns, female, male column. And so the degrees of freedom associated with our table is 3 minus 1 times 2 minus 1, which turns out to be 2 times 1, which is 2. So what we could do is we could try to find out what's the probability of getting 3.73 or more if the degrees of freedom is 2. And there turns out to be a little function in TigerStats that'll let you do that. It's called P chi-square GC, probabilities for chi-squared curves GC. All you have to do is put in your boundary number, say region is above. It's just like using P norm GC. You got to say the degrees of freedom and go ahead and get a graph of the chance. And if you were to run that in the console in RStudio, you would get this picture in your plots window and you would get this number in the console. The chance is about 15.5%. So that's our p-value. So again, just think about this. If the null is right, if seating preference and sex don't have anything to do with each other, there's about a 15.5% chance of getting a chi-square statistic that's as big as the one we got. Now, You don't have to do this in pieces. You don't have to do these calculations in pieces. There is a function in TigerStats that'll do it all for you. ChiSquare Test GC, the same one as in section 6.3 for goodness of fit. But you can use it to test independence of two variables. You just change up your formula a little bit. Your formula starts with a twiddles. Then you put your explanatory variable. Then you put your response variable with a plus in between. And you got to say what data set those variables live in. And the graph equals true is going to give you that picture of the p-value. So let's go ahead and let's run this in RStudio just to remind you this is something you should keep on doing for practice. So got it in my console, I run. And so there's a lot of output that we're going to need to be looking at here. Here's the graph of the p-value. So we look at that output in pieces. It starts off by saying, here's what we saw in the data. And so it's that same tally table we were looking at, except you've got the sex going along the rows instead of columns. And here's the kind of table the null was expecting to approximately see, this one here. And so there's these differences. And then it goes on to say, let's make our chi-square statistic. And so it computes the little fractions, observed minus expected squared divided by expected, for each of the 6 cells. And here they are, it's these 6 numbers. The chi-square statistic is those 6 numbers added up. That's the 3.734. The more difference there is between the observed and the expected tables, the bigger these numbers in here are going to be, and so the bigger the chi-square statistic is going to be. Now, it does tell you the degrees of freedom of the table is 2, and so that means that you know to say to yourself, hey, if the null's right, we would expect the chi-square statistic to be around 2. It actually turned out to be 3.7. Is that an unusually big number if the null is right? Going along further, the output helps us with that question because it gives us the p-value, the 0.1546 that we saw earlier with p-chi-squared GC. So if the null is right, there's about a 15.5% chance of getting results like what we got. That's a reasonably big chance. We don't generally reject the null hypothesis unless the chance is a good bit smaller. Less than 5% is our usual level of significance. So our decision this time is that we won't reject the null hypothesis. That simple non-technical conclusion that I want you to provide, the one that says how strong is your evidence in the data, against the null and for the alternative, well, this time we would say our data did not provide strong evidence for that alternative. It did not provide strong evidence that sex and seating preference are related. For all we know, they could have nothing to do with each other out there in the population, in spite of the differences that we found in our table. I want to talk about something that can happen when you apply the chi-square test for independence. And we'll pick it up with another example from M11 survey. There's another column of interest, and it's how the person reports feeling about their weight, whether they feel underweight, about right, or overweight. And I'm wondering, are seating preference and how you feel about your weight, are they related out there in the population where this data came from? And so again, you set up hypotheses. In a chi-square for independence test, the null is always going to say that the two variables are independent. And the alternative will always say they're related. And so you just, you can run your standard code that we learned. So explanatory variable seat, response variable weight feel. in this case, like, I don't really know if one of them is more likely explanatory than the other, so I just kind of picked an arbitrary order. But let me give it a try. Here we are in the console. We run it. I didn't say graph is true, so I don't have any new plot over here. And, I get this kind of similar output to what we saw last time, all the way down to the p-value. But there's this little message at the end, and that needs to be addressed. Some expected cell counts are low. The approximation of the p-value may be unreliable. Consider using simulation. So what was going on with that? Well, remember that the math theory says that the chi-square statistic only approximately has the chi-square distribution, the one given by one of those curves. And the approximation is better the bigger the sample size is, but it needs to be big. The sample needs to be big enough to make those expected cell counts at least 5. And when we look at the expected cell counts in the output, when we ran that test, we see that there are several of them. This one here, this one here, this one here, this one here, that's not at least 5. So our sample really isn't big enough to make that approximation a trustworthy one to use when we find p-values. So what do? Well, when we first learned about the chi-square test, we learned that we could find p-values by simulation, where you have the computer set up a little scenario where the null hypothesis is actually true, and then you pretend to take samples of the same size as the ones we actually took in that scenario. And you do it a lot of times, and you compute the chi-square statistic each time, and you keep track of how many times it came out bigger than the chi-square statistic we actually got with our data. We can do the same thing here in the dependent situation. We just have to tell ChiSquare Test GC to do that. So we start off the same way, where we do twiddles, one variable plus the other, and we say where those two variables live. But then we say simulate.p.value is true. And we also say how many of these simulations do we want? Let's say 3,000. And for fun, let's get a little graph of how those simulations came out. So why don't we try this at the console? And so you get some similar output that we're going to need to analyze. Notice there's no warning at the bottom. And we get this plot over in the plot window. And let's talk about it bit by bit. So once again, you get your observed and your expected cell counts. And let's take a close look at them now. Here's what we saw in the data. So like there were 3 underweight people who preferred the front. There were 4 people who thought they were underweight that preferred the middle, and so on. Compare each of these numbers to what the null hypothesis would expect to see if you took a sample of size 71 out of some population where these 2 variables have nothing to do with each other. 3 versus 3.42, not a big difference. 4 versus 4.06, not a big difference. I mean, you can trawl around a little bit, and I don't even see like anywhere where there was really a big difference between what the null expects and what we actually got. So as you might expect, if you add up all of the contributions that go into the chi-square statistic, you don't get a big number. It turned out to be about 2.09. Now the degrees of freedom of the table is, again, number of rows minus 1, so that's a 2, times number of columns minus 1. And so that is also a 2, because there's 3 columns. 2 times 2 is 4. And so the degrees of freedom is 4. So that math theory says if the null is right, if seeding preference and feeling about weight are independent out there in the population, then we would expect the chi-square statistic to be about 4. Now, it turned out to be about 2.093, and so it's not even bigger than 4, It's certainly not a lot bigger than 4. And so we could check our simulations to see, like, what's the chance of getting bigger than or equal to, a 2.0973 like what we got if the null is right. And it's a pretty big chance. It's like about a 75.87% chance. The graph is showing you that. That's a histogram of all the 3,000 resampled chi-square statistics where the machine is like doing this little sample of size 71 every time from a population where it doesn't, where there's nothing, where seeding preference and your feeling about your weight don't have anything to do with each other. And, it got bigger than 2.09, which is this red line, lots of the time, 75.87% of the time. So the p-value is, 75%. That's way bigger than 5%. We are totally going to fail to reject the null hypothesis here. Here's our conclusion. This data did not provide strong evidence that seeding preference and feeling about weight are related in this population. So, as usual, a test of hypothesis is going to involve your standard 4 steps. For the chi-square, you've got to do your preparation. You need to state those hypotheses. You don't have to identify any parameters. There actually are ways to have multiple parameters that state what it means for two variables to be independent. But you can read in the textbook about how they try to state that. It's not a big deal for you to do. Null says the two variables are independent. Alternative says they're related. You do need to do the check, and fortunately, ChiSquare Test GC is going to do that check so that you can see, are the expected cell counts bigger than or equal to 5? Always check. So if the check fails, you're going to need to rerun with simulation. Now, once you've got things going, you look at the calculations that R has done for you. You look at the test statistic, you look at the p-value, and then based on the p-value, you go to your conclude step where you decide what to do about the null hypothesis, and then you write that simple non-technical conclusion. Okay, a lot of typos in this set of slides, so I'm going to go back and fix them, and by the time you get to see them, they won't be there, I hope. That's about it. See you later.